Okay, let's begin. So, in the last class, we looked at that five transistor OTA. So, hopefully, yeah, I've copied it already. So, this is that guy. So, for this guy, first we looked at the DC operating point, and we observed that although the circuit is asymmetrical, by contradiction, we proved that the stable operating point here is to have the currents in the both arms to be exactly equal. And then we found the small signal gain, and that we computed as product of the short circuit transconductors and the output resistance. And in this, for this circuit, what was the short circuit transconductance approximately? It's a GM of this guy. And that should also make sense because that is the transistor that converts the input voltage to a current. And what was the output resistance? What is the output resistance here? It's basically parallel combination of these two output resistors. Again, although it appears that it is parallel combination of these two, it doesn't necessarily mean that. I mean, it doesn't mean that looking up the impedances R02, looking down it's R04 and so on. Okay. And then we kind of looked at the range of voltages we can apply at the input so that all transistors lie in saturation region. So that was the input common mode range. And yeah, I gave output common mode range as an exercise for you to work out. And then we sort of put it in negative feedback and we started to see what's going to happen. So let's pick it up from that point. So again, in the last class, we kind of considered an ideal OTA. By that, we assume that it has some GM, but it has an infinite output resistance. We put it in negative feedback like this, and we decided to apply an input step. And a single stage OTA, as we saw, is more suited to drive a capacitive load. Right. So here again, what was the output? If I call this as the output voltage, and if we assume all the capacitors are initially uncharged, what was V out at 0 plus 0? Right. Again, this again we proved simply by contradiction because if the capacitor voltage has to change abruptly, the current flowing through the capacitor must be an impulse. And in this circuit, what is the current flowing through the capacitor? If I call I out, yeah, I out of t is what? It's basically fixed by the transconductor, which is this guy minus P out of t. So which means if the output voltage changes as a step, the current will also be a step, so it can't be an impulse. So simple contradiction. And similarly, what is the current at 0 plus? It's Gm delta V. Again, V out is 0, T equal to 0 plus, so current is simply Gm delta V. And what happens as T tends to infinite? Hmm? What is V out as T tends to infinity? It asymptotically approaches and reaches delta V. And what is the current? Okay. Cool. And by the way, okay, that maybe should point out this. So let's say I have an ideal op amp and I do the same experiment. Yes, I put it in negative feedback like this, have an output capacitor as a load, apply a delta V step. Hmm? And remember, by definition, an ideal op amp is what kind of control source? Voltage control? Voltage source. Okay. But I mean, we have made a voltage control current source, right? So let us say I do this experiment. So here, can you tell me what is V out of 0 plus? Huh? Why 0? Why delta V? Why not 0? Yeah, why? Okay, see, again, we can assume that let's say V out changes as a step. What should be the current? Impulse. And remember, this is a voltage control voltage source. So if I actually were to draw, yeah, it like this. So basically, this is the control source, the output capacitor, and then we are going and doing it in feedback like this. So this is a voltage source. This can supply any amount of current. Okay. So this can provide that infinite impulse current. So it means output will jump instantly to delta V. Is that clear? I mean, the crucial difference is when we have an OTA, I mean, although the OTA by itself has no limitations in current, okay, it can provide any amount of current. But the problem is the current is kind of fixed by this relation, right? Because the current is fixed by this relation, you can't have an abrupt jumps in the capacitor voltage. Okay. But if you have an ideal OTA, sorry, ideal op amp, by op amp I mean voltage control voltage source, it will respond instantaneously to any instantaneous step in the input. Okay. So this will immediately jump to delta V. Right. So basically, if you have, yeah, I mean, if I were to sketch the two, we'll do it here. With a VCVS, we'll have something like this. But with a VCCS, we will have an exponentially rising behavior. Is that clear? Again, this is a first order exponential behavior. So what is the time constant here? Sort of computed. What was the time constant? I mean, it is basically the capacitor times the resistor we see here. What is the resistance we see looking here? No, no. Huh? Yeah, yeah. I mean, what is the resistance alone? If I call it Rx, what is Rx? Just 1 by gm. Again, remember that this is identical to this scenario. If you take a transistor, connect its gate and drain, I'm sure everyone remembers this impedance is 1 by gm. It is the same old, right? I mean, this is minus terminal, plus terminal for the OT. So the time constant was computed as this. So of course, this was it. Okay, in VCVS, see see VCVS, what is getting fixed here is the output voltage. There is no, what do you say? There is no limitation or not limitation. There is no equation that governs the current as such. Only the voltage is fixed. It is a voltage source. To sustain that voltage, it can provide any amount of current. Yeah. Whereas here, right? Yeah. Here, the only thing that needs to be satisfied is this current should go to zero in a steady state. No, it is there, right? That's what. But it takes some time. See, here, this current will eventually, I mean, this will eventually go to zero, which means P out will go to delta V. But the point is, it doesn't act instantaneously. It takes some time to settle. Virtual ground is there, but it is all steady state. But with an ideal VCVS, it is all infinitely fast. I mean, other way to think is, see, if you have a voltage source, I put any load here, nothing is going to change. The voltage is going to be fixed, right? But with the current source, things will depend on the output load, right? So this capacitor will not load this guy here because it's an ideal voltage source. You put a dinosaur there, it's going to maintain the same voltage. But that's not the case with the current source. Is that point clear? Cool. So yeah, in the last class, we tried to compute what is the maximum slope of V out. And the motivation is, again, with if it were an ideal op amp, it's going to jump instantly. But now it's going to rise with some finite whatever, right? So you wanted to see how fast it can rise. And at what time instant this rises with the maximum slope? Huh? Look at this curve. At what time instant the slope seems to be maximum? 0 plus. And what was the slope? I mean, again, you don't have to compute. You can look at it here. At 0 plus, what is the current? So if I had to go to next page, maybe. At 0 plus, we have current Gm delta V getting pushed into the capacitor CL. So what is the slope? we have a constant current getting pushed into a capacitor. The output will ramp up. And what is that slope of the ramp? It is the current at, it is the current value, which is Gm delta V by CL. Again, this is something we did in the last class. Okay, and yeah, take it as an exercise and repeat the same calculation, assuming finite R out. Assume R out is some R naught and repeat. Okay. Because I have ignored the intrinsic output resistance here, so do it yourself. Cool. So now we know what will happen if you have an ideal OTA and put it in negative feedback. Let's try to see what will happen with our five-transistor OTA. So this is so yeah, this is the output voltage. We know what is the plus and minus terminal here. What is plus terminal? Yeah, so again, if you not clear, if I increase this voltage, what will happen to this drain voltage? That will decrease because again, if you increase the gate voltage, you'll be drawing more current. You pull out more current from a node, that voltage drops. So this voltage also drops. So which means this voltage, if the gate voltage of the PMOS reduces, what can you say about the current? Current will increase. You are pushing in more current into this node. What will happen to the voltage? Increase. So what is the plus terminal? Left side or right side? Okay. So this is the minus side. This is the plus side. So put it in negative feedback. I'll make a connection like this. Okay. And at the plus side, I'm going to apply the step feed. Okay. Okay. For simplicity, I'll assume the current source is ideal. That will reduce the complications. Okay. So again, we are trying to find the same thing. This is the output. What is the maximum slope with which the output rises? And we know that that is going to happen at what time instant? 0 plus. So let me try to take a snapshot of this circuit at 0 plus. Okay, at t equal to 0 plus, we already know what is the output. Output is 0. Incrementally, it is 0. So which means if I measure the total voltage, it's going to be the VCM. Okay, cool. And okay. And what is this voltage at t equal to 0 plus? It's not a trick question. No. It's VCM plus delta by U of t at t equal to 0 plus. Sorry. Yeah, so now you see, if I mark these two currents as say I1, I2, which of the two currents do you think will be higher? I1, because gate voltage is higher, so I1 is greater than I2. But what can you say about the sum of the two currents? That has to be I0 fixed by the current source. So now I know that if I apply a delta V step, I2 is going to be smaller, I1 is going to be larger. So if I keep increasing delta V, that is, if I keep increasing the input step I'm applying, what can you say about the currents? Right? And at some point, what will happen? At some point, I2 is going to become 0. Right? So I'll say at some delta V equal to a max delta V, I2 will be 0. No, that okay. Okay, I1 is increasing, that is okay. But the sum of the two currents is, right? So if I1 increases, to keep the sum same, I2 automatically has to drop. You understand? Yeah, it's the total current. Okay. That's why I've written every voltage clearly, right? It is VCM plus delta V, it's VCM.
That delta V causes an incremental current to appear in M1, right?
Yeah.
And VCM does not contribute to any incremental current. So
No.
So like appearance of delta I, is it like the delta I is in fact affecting the quiescent condition?
No. I mean, see, if you look at the total current, right? Nominally, you have I naught by two, I naught by two, right? The moment you apply a step, this guy, let us say, is going to have a GM delta V. So this will be
Mhm.
okay. So that's what I'm saying. This is the total current, I1, I2. Is this okay? I mean, I'm not even going to small signal, right? If you even look at logically, without knowing anything, right? This seems logical. Sum of the two currents is constant. If one current increases, other has to drop. Okay.
So, but considering the equation that
Mhm.
k times the VGS
Fine,
for
fine.
the
Yeah.
capacitor,
Mhm.
so like the VGS for M2 isn't changing.
No. Why not changing? What happens to Vx? Right? That we have not computed, but that's going to change. Right? That's how it happens. So is this clear? At some delta V max, I2 will become 0. So which means what can you say about M2? What operating region is it in? It just enters cutoff. So which means I will say all of the current I naught is getting steered to M1. Okay. So at this delta V max, the current here is 0. Well, maybe remove this. So this is not operational, and all the current kind of flows here, right? And this current also flows here, I naught. And these two are form a current mirror. So what is the current flowing in M4? I naught. So what is the current flowing to the output? Right? Because bottom, no current flows. I can basically say it's sort of disconnected. Okay. So the entire current flows through the output. So what is the maximum current that can flow to the output capacitor? So what is the maximum slope with which the output can rise? I naught by CL. Okay. So in this case, yeah. But the thing is, this source voltage will keep increasing, right? Diode connected, but for cutoff, what is the condition? VGS has to be, this is sort of fixed. I'm looking at T equal to 0 plus alone. At T equal to 0 plus, the gate voltage is fixed. But if you keep increasing this voltage, this will try to follow it, and it will go out as whatever, active condition. That's a good question. Is that clear? Yeah. Yeah, I mean, it will go to some voltage so that M2 goes to cutoff. What voltage will it will go to, we'll see. But it is clear that if this increases, this will also try to increase. That will take this out of. Huh? Yeah. Yeah. That's all. Okay. So basically, what this means is that, see, ideally, if we apply a step delta V, we expect a nice exponential settling like this. Okay. Now, if I apply a voltage delta V, which is, let us say, delta V prime greater than delta V max, if it were an ideal OTA, the output will be a scaled version of the same curve, right? But now, what's happening is the voltage you applied is so large that the current demanded at T equal to 0 plus is much greater than what is the current available in the OTA. So the OTA is trying to push all of its current to the output and try to charge the capacitor. Okay. So if you apply a large enough step, M2 is going to remain in cutoff initially. So which means in the initial portion, the output capacitor is going to get charged with a constant current I naught. Is that fine? So if the output is, I mean, if the current flowing through the capacitor is constant, how do you think the output voltage will change? Constant current getting pushed into a capacitor, output sort of ramps up like this. Okay. So it will ramp up and this will continue till M2 is in cutoff. Okay. So slowly this output voltage increases. So which means after some time, M2 will start conducting. Everything will be in saturation, and then you expect the exponential settling later. So till this point, let us say it will do this, and after this you will have the same exponential settling. Okay. So I mean, so which means even if you apply a voltage say to delta V prime, which is obviously greater than delta V max, at t equal to 0 plus, what can you say about the current flowing to the capacitor? It will still be I naught. Okay. So even for this voltage, ideally you expected something like this. But now how will it go? Initially it will go with a straight line like this. So since the step is larger, it will remain in this region for a longer time. And say after this point, M2 starts conducting, and then you will have, let us say, exponential. Is that okay? So again, this would not have happened if this were an ideal OTA, right? With an ideal OTA, we didn't have any limitations on the output current, which means it can provide any amount of current. So for any step, it would have been a nice exponential settling. But with a real OTA, this will happen. I mean, this could happen. So basically, yeah, one couple of terminologies. So this is called slewing, and this rate is called slew rate. We'll denote it as SR for slew rate, and I'll say it's SR plus, so that to denote that this is showing how the output is increasing, right? Because we can also have a negative step. So this is slew rate, and this process is called slewing, where the output, instead of rising exponentially, it rises linearly for a short time. Right? And obviously, as you can see, this is not good with respect to the settling time, because ideally you expected output to have settled here, but it's going to take longer. And number two, this will come to it in the second half of the course. See, so do you think this with slewing, this is the output you get for two different values of input? Do you think this is a linear phenomenon or a non-linear phenomenon? No, I mean, what I'm saying is I applied a input of delta V prime. Okay, maybe I'll use the same color. I applied a voltage delta V prime, right? I got something like this. This is linear. Okay. I then applied twice that voltage. I have the same thing and then doing this. If I have a input output relation like this, do you think this is linear or non-linear? Right? Because remember, if input scales by 2, you also expect this curve to be scaled by 2. That's not happening. So that's straight away introducing non-linearity. Okay, that is again a problem. We'll come to it later. Okay. Yeah. So again, this is the positive slew rate. Similarly, you can find a negative slew rate. This one. What is the intuition behind the longer linear time for greater delta V? Okay. See, if we apply a higher delta V, the source voltage is going to increase too much. So which means, I mean, this transistor is going to enter whatever, it's going to start conducting only after the output voltage exceeds the source voltage, right? For a larger step, source voltage would have jumped up higher. So which means it will take longer time for the output to rise beyond that. That's right? What happens to Vx is like it equal to 0 plus, it instantly rises to a particular value. Right. Until the time we have that linear kind of region, it remains there. Yeah, exactly. The second MOSFET, M2 will wait till the time it has sufficient VGS. Yeah, exactly. So yeah, let's quickly look at the negative slew rate. Again, I'll form the negative feedback. So for negative slew rate, what I'll assume is I'm applying a delta V, I mean minus delta V. So here, which of the currents will be smaller? Current flowing in which transistor is going to be smaller? So again, if I apply a delta V max, which current will be 0? this current is going to be 0. So which means all the current is going to flow here. So again, this current is 0. So which means this current is 0. This current is 0. So what is the maximum rate at which the output kind of drops down? It's the same I naught by CL. Earlier we were pushing in a current I naught. Now we are sinking in a current of I naught. So the negative slew rate is also I naught by CL. It's in this case turns out to be equal to the positive slew rate also. This need not be the case always. In this OTA, it turns out to be the case. As we'll see in some other topologies, this need not hold good. Okay, so one related thing about this. So let's say I take this guy. Now here, let us say I go and apply the step delta V, or I apply a delta V change between the two gate voltages in this 5-transistor OTA. Okay. And then I try to plot this curve. The difference between the currents I1 and I2 versus the applied delta V. If delta V is 0, what can you say about the current difference? 0. Yeah. VCM is there. In addition to it, basically the two gate voltages have a difference of delta V. It is not, sorry? No, no. And it is also biased appropriately. Okay, the VCM is there for biasing, right? That is there. Okay. Yeah. Uh-huh. You are saying that you want to flip this connection. There is no difference, right? Now it is as though I have flipped it, over this axis. Basically, this is now your M3, this is now your M4. Right? Nothing has changed. Yeah. No, now this will not copy this current. You see, remember that the current mirror is basically any current flowing in this diode connected device that gets mirrored here. It's not the other way around. Okay. Yeah. So again, if delta V is 0, this is 0. For a small delta V, what can you say about the difference in the currents? Okay, let's not make it so crude approximation. Yeah, linear. What will be the slope? Okay, see, again, if you think about it, this is basically same as finding the short circuit current, right? That is, let me just quickly see. When we try to find the short circuit transconductance, we kind of shorted the output, right? That was incremental short. So which means if you had to actually go and measure it, what would you connect it to? This has to be incremental short. But I will not connect it to 0 volts, right? What will I connect it to? No, no. My question is, let's say I want to find the short circuit current here to find the short circuit transconductance. Let's say you want to measure a short circuit transconductance here. So the point is, we know we have to incrementally short this point. Incremental shorting means this voltage should be a constant DC voltage. So what voltage you might connect it to? Whatever the nominal voltage is, you will try to connect it to that, right? So what is the nominal voltage? What is this voltage nominally? Okay, see if let's say this is the OTA. Ignore this delta V, right? In quiescent condition, what is this voltage? VDD minus VSG of at the current of, and what is this voltage? Again, by kind of contradiction, we proved that this should be same as this. So to find the short circuit current, you might basically connect it to the same voltage, right? Okay. Remember that incrementally it has to be short, which means it has to be maintained at the same quiescent. Okay. So now you try to measure this current. That's how you'll be measuring short circuit transconductance. If you are given an OTA and asked to measure the short circuit GM, this is what you would do in the lab, right? And now we can see, so what is the current flowing here? If the current here is I1, what is the current here? What is the current here? So what is the current flowing out? So, I mean, I'm sort of indirectly measuring the short circuit current here. Okay. So now tell me what will be the slope. For a small delta V, what will be the I1 minus I2? I mean, I1 minus I2 is the short circuit current. How is it related to delta V? No. See, you know that if you apply delta V, the short circuit transconductance times delta V is the output current. It is a short circuit current, right? That short circuit current is what is I1 minus I2 here. Okay. And what is the short circuit GM in this OTA? GM of M1 or M2, right? So basically for small delta V, it's going to rise as GM1 like this. And let us say I reach a delta V max. What happens? I mean, at delta V max, we saw one transistor goes to cutoff. So entire current flows to one branch. So this saturates to. So, okay, maybe I should not. Okay, maybe there's something like this. Similarly, in the negative thing, it will do the same thing, right? This is minus I naught.
Essentially not stays linear till a longer duration of delta V.
I mean, longer is all relative, right? For this range, it looks linear. Right? Okay. Cool. So, yeah, okay, one more thing. Let's quickly find out what is this delta V max, right? Maybe that also we can do. For that, yeah, let me use this. Yeah, I know that at delta V max, these two are going to happen. Okay, solve this. So M2 is just entering cutoff at delta V max. So what can you say about the gate to source voltage of M2? It is just entered cutoff, VTH2. The gate voltage is VCM. So what can you say about the source voltage? We'll remove this. So Vx is fine. And what is the current flowing through M1? Huh? I naught. So which means what can you say about this voltage? No, I mean this, it's VGS of M1. Okay. So the gate voltage is delta V max. Okay. So now what is this one? VGS1 at a current of I naught. This is the gate voltage. This VCM plus delta V max minus the source voltage. Fine. So what is delta V max? VGS1 minus VTS2. But what can you say about the threshold voltages of M1 and M2? Will they be same or different? Or one? Huh? Why? I mean, identical, and threshold voltage depends on the source to bulk voltage. They have a same source voltage, so it's same. So this I can change it as VTH1 also.
Can you please reiterate the part of VCM and
This one?
second? Yeah.
Okay, I see. This is fine, right? This is the source voltage, right? And what I'm saying is VGS is the gate minus source voltage. So yeah, so delta V max is VGS1 minus VTH1 at a current of I naught. That is basically the overdrive of 1. And nominally, what is the current flowing through M1 and M2? I mean, nominally, what is the current I naught by 2? So what is the overdrive voltage at a current of I naught by 2 in terms of whatever transistor parameters? Yeah, root of it's just okay. I don't speak. So 2 I naught by 2 by what mu n C ox W by L of 1. Right. So now can you relate overdrive at a current I naught to overdrive at a current of I naught by 2? 2 times this. So I can write it as square root 2 times. So it's the delta V max is basically square root 2 times the nominal overdrive voltage of your main differential pair M1 M2. Okay, so any step within that it is fine. If the input step is greater than this voltage, then one transistor goes to cutoff. Okay, okay, so a couple of things I wanted to talk about this 5-transistor OTA. Let me copy it if I have a clean copy somewhere. Okay, so let's say let's say this is an ideal current source for now. Let's look at some small signal impedances here. Let's say in particular, I'm interested to find the small signal impedance looking into the source node. So again, in small signal, current source is open. The supply is incrementally ground. So these are also incrementally ground. Okay. Erase these things. Okay. So to find the small signal resistance, I'm going to apply a test voltage. I'll try to measure the test current. Now, obviously, this current flows in both halves, say I1, I2. I'm interested to find the impedance here. Okay. That's let's say, I don't know, RS. Let's say RS is something. I mean, you're given something, you should understand what impedances are at each node, right? You can take it as an academic exercise, right? But later on, we'll find these things handy, right? Yeah, okay. So the current is going to split in the two halves. So which of the two currents do you think will be higher? Whose VGS is high here? Huh? But remember, current also depends on what? VDS. So which of the drain voltages is higher? Okay, so let's again assume. Uh-huh. Okay, we'll come to that. Okay, so okay, let's say I1 is greater than I2, right? And if I quickly draw the small signal, we'll have this here. What is this current? Minus GMVT. Similarly, we have the same thing here. What is this current? And this also the same or not. So again, it's all the same thing, right? Current depends on gate to source voltage and drain to source voltage. That's all. So if I1 is greater than I2, and I know these two currents are equal, which of the two voltages has to be smaller? V3 or V4? Let me mark it clearly. V3, V4. I'm saying this current is greater than this current. Left side current going up is greater than the right side current going up. So which this voltage greater or this voltage greater? V3 has to be smaller than V4. Fine. Right. So now let's also look at the top side. So again, if I draw it like this, what can you say about these two currents? They'll be same. GM, VGS, right? Both of them have the same gate voltage, same source voltage. Fine. So, and I'm saying that this voltage is smaller than this voltage. So what can you say about the current I3 and I4? So V3 is smaller than V4. I3 has to be smaller than I4. Fine. But what can you say about I3 and I1? They have to be equal. So which means this means, so again, it's a contradiction. I mean, once again, see, this is same thing as we did for the operating point, right? The only difference is this is a small signal model, so which means the relations between current and voltages are linear. That's the only difference. Otherwise, the same argument. Okay. So what can you say about V3 and V4 then? They have to be equal. This is the same thing that we did for the operating point currents. Okay. Mhm. Yeah, but the thing is current mirror, but you also have the dependence due to the drain to source voltage, isn't it? Right? So that's the whole, that's what makes it slightly involved. So let's actually draw it neatly. Okay, I have to copy this. So which means if I do this, V3 is same as V4. So if I find that these two voltages are same, what can I do? You can basically go and short it, right? Again, this incremental short, let me mark it there. So now you see that these two guys are put in parallel, and these two guys are also in parallel. So we have something like this. This is, I'll say 2 times M3, say 2 times M4. This is 2 times M2. And then you have the test voltage. So what is the resistance looking here? Okay, I mean, remember if M4 has a GM of GM4, this is 2 transistors of M4 put in parallel. So what is effective GM? Okay, I mean, let's also take it, let's look at a simpler case. What is the impedance here? What I'm doing, I'm taking one more copy, putting them in parallel, right? So this is 1 by GM, this is 1 by GM. I put the two in parallel, what happens? So what happens to the GM? No, GM doubles. Is that fine? Okay, maybe this is a thing, right? See, I also know that GM is, this is fine, everyone has seen this, right? So I'm increasing the width by 2. Shouldn't GM increase only by square root 2? That's the thing, right? See, here, the moment I put the two in parallel, if one guy carries a current I, when I put two in parallel, the current is 2 times I. So we're not just increasing the width. This doubles, yes, but this also doubles. So that is why, GM doubles. And in fact, in these scenarios, what is a better expression to use for GM? No, see, I think you see here, right? When I do this experiment, what doesn't change? Current changes. What doesn't change? VGS doesn't change because I'm putting the two in parallel. I mean, if I take two transistors, I'm basically doing this. I'm putting the two in parallel. What doesn't change is the voltages, VGS and VDS. So what is a better expression to use for GM? Yeah, this is this guy, right? W by L into. So here it comes out directly. I mean, you can use any expression, but you should be clear. as to what all change in your circuit. I mean, the extreme cases, you can also say GM is 2 ID by VGS minus VT. And if you are ignorant, you will say this doesn't depend on the width. Right? And remember, this nothing to do with circuits, right? It's a simple math, right? And in fact, I mentioned this because this was one of the questions asked for my friend in his IMA interview. Not even related to this. In IMA, as basic math, he was asked this. Right? It's basic logic. So anyways, let's get to this. So what is the impedance here? Okay, sorry, mu n C ox. Oh, okay. I didn't realize this is getting cut. This is mu n C ox W by L into VGS minus VTH. Okay, I didn't realize. Sorry. So what is the impedance looking here? 1 by 2 GM. So the resist 2 GM4. So the resistor at the drain is smaller than the resistor R0. So what is the overall impedance here? 1 by? I mean, this is basically what kind of configuration we have. Oh. Okay, let me take it to one more page. We have something like this. I am trying to find the resistance looking here. Resistance looking into the source. So what is that? Huh?
R1 plus R2.
No. I mean, under some conditions we saw upper resistance is very less, and that is in this case it is 1 by 2 GM4. The upper resistance should be smaller than the R0 of the transistor. In that case, what is the impedance looking? Just let us say M2, it's 1 by 2 GM. Okay. I mean, this is basically your common gate, right? We saw if the drain was exactly short, this is 1 by GM. The moment I had a resistor, the looking in impedance depends on R0 also. And I asked you to work out what that was, blah, blah. But the point is, if the drain resistor is smaller than the R0 of the transistor, looking impedance here is 1 by GM. Fine. So yeah, this resistance looking here is 1 by 2G. I mean, in fact, here you can probably should have done this. Looking here is basically 1 by GM. Looking here is 1 by GM. 1 by 2 GM. That's a simpler way.
GM2 come when we calculate M2 resistance, GM2 comes with parallel with R0.
No. See, that's the thing, right? See, if you have this, yeah, here it as an exercise. So please work out and see if this impedance, if this is the case, you will find that if this resistor is smaller than the R0 of this transistor, approximately the resistor is 1 by 2 GM. I mean 1 by GM. This is not exact, approximate, and these approximations are very good. As long as the drain resistor is much smaller than R0. Okay. Okay, so less time, but let me also cover this. Let's see. So let me also try to find, this is open. So now let us say I try to find the resistor looking here. Okay. At this node. So I apply a test voltage. What do you think the resistance is? These are all short. What is the resistance do you think looking here? MSR, no. R out is, this is R out. Yeah. But why should that be R? Here I have a different connection, right? No, I mean, what? Huh? Yeah, diode connected. So what do you think the resistance is? Yeah, it is very tempting to say 1 by GM, but let's also. That's the thing, right? See, if you again quickly draw the small signal, I have what is the GM VGS of this transistor M3? This is test voltage VT. Let's say GM3 VT. In addition to that, I'll also have R0. What is the current? R03. But remember, this VT is also applied to the other side. In the other side also you have a current of what? Let's say GM4 and GM3 are equal. Okay. And this current, So basically, no, this is not VT by R naught. This current is this voltage by R naught. Okay. So we have again another R naught of, let us say, 4. So notice that this current can either flow here or here, right? And whatever current flows down, and that will contribute to the test current. Okay. So I mean, maybe for simplicity, I will say this is minus GM3VT and change the direction. So now you see this current splits between this resistance and this resistance. You are interested to find the current flowing here, right? And I mean, what if you remember what is the resistance looking down? We calculated last class. It's basically 2 times the or not 2. Okay. So now it's a current division. This current splits between these two resistors. So what is the current Ix here? Minus GM3VT is the current times. Yeah, just a second. So everything went off. So Ix is minus GM3VT times current division. So what is the total test current? Now can you tell me? This is the total test current. It has a GM3VT, this current. You also have, say, VT by R03, that is small. And then minus Ix, right? And that basically is plus GM3VT. Okay. And again, if GM3 is greater than 1 by R0, this can approximate it as GM3 into 1 plus this. So the resistance is what? This I test. What is the resistance? It's 1 by GM3, but into 1 plus this factor. Okay. Again, this all happening because this is an asymmetrical circuit, so should be slightly more careful. It is very tempting to say this impedance is 1 by GM, but yeah, I mean, it's completely not the case. In fact, here, right, if I take a degenerate case where, say, R04 alone tends to infinity, what does it tend to? No, no. Can you look carefully? Oh, sorry. Oh, let me take it to the next page. So the resistance was 1 by GM3 into 1 plus. Okay. So here I'm saying, let us say you allow tend only R04 to infinity. What happens? 1 by, right? Again, this yeah, special case. So yeah, I think that's with the class. So can discuss some tutorial questions. So I'll just discuss one question and I'll hand it over to the TS. The one question is this. I think you're asked to find the resistance looking here, right? Hmm. So again, see here, usually you're given a circuit. So simplest thing to do is ignore some non-idealities and see what is the ideal result you should expect, right? So here, what I can ignore first? I can ignore R0. So let us say R0 tends to infinity. You apply some test voltage here. So gate voltage is also the same. I've ignored the R0, so which means current depends only on, yeah, gate to source voltage. So what is the current, drain current here? GMVT. So the test current is also GMVT. What is the resistance? So ideally, this is what you should get. But with R0 also, you can quickly find it. It's a no-brainer. See, I'll take it to, can write it here maybe, yeah. With R0 also, if you calculate it, see, one thing you can do is the following, right? This is what you're supposed to do, apply V-test and find the current. I can think of it like this. I have two different excitations. Right? And then I'll find both currents and add up. Anyways, this is trivial because this current is 0. So I just have to find this current. So we have a linear network, two inputs. What do? Superposition. So let us say I find only the contribution due to the gate. So what will I do? I'll take it to the next page maybe. So I'll short this guy. Right? So I have what? Gm times Vt or not. I'm interested to find the current here. What is that current? I mean, this current, it's a current division, right? I have a current GMVT, which can either get divided between R naught or R. I'm interested to find the current flowing through R. So what is that current? Done. So second thing is to find the contribution due to the drain. So which means I'll go and short the gate. If I short the gate, what is the effective? It is just R naught. So I can basically go and replace it with an R naught. So what is the current? VT by? It's basically these two resistors in series. That's all. So what is effective resistance? This is the test current. So you'll find this to be R plus R naught. So again, in R naught tends to infinity, what happens to this? 1 by Gm. So again, so actually this should have struck you. So I have a case where the resistance is this, right? And which means if my R is much, much smaller than R naught, the resistance is, does it resemble of, I mean, does it remind you of something? What it means? So you had, if you, so in a common gate, I mean, you work out these two and try to, like form parallel between the two, right? Then you'll understand. You'll see. Okay, so which means now if I have something like this, I know what is the resistance looking here, right? Okay. And in fact, maybe I'll just iterate this point. See, if let us say I don't make this connection, so how many terminals are there for me in the network? 3 terminals. If we have a 3-terminal device, how many port network is it? Remember, a port by definition is a pair of terminals. So how many ports I can define? 2 ports. I can say this as a common port. So for small signals, it is linear. For a linear 2-port network, how many parameters I need to characterize it completely? Right? Again, if you take Y parameters, for example, if this is I1, I2, I1 and I2 will be linearly related to V1 and V2. So we need 4 parameters. So now I go and make this connection. How many terminals I have? So how many port network is it? So for a 1-port network, how many parameters I need to characterize? Y2. I mean, it's a 1-port network. It's a linear network. So current is linearly related to the voltage. Only one parameter. And what is that parameter? The resistance. You've already computed that. So which means anytime you go and see this guy, you can go and replace it with a resistor. Yeah, I mean, approximately 1 by Gm, but exact resistance is fine. So I think extensions of this was given in your assignment, right? So one question was to find the resistance. I think was this, and then you had something here. So now tell me, what is the resistance? I mean, see, don't complicate. what I told, this is a one port network. What is a it's a resistor. This I can replace with a single resistor, approximately 1 by gm. Again, let's take the exact expression if you want. So it's R plus R naught. And then I have the bottom side. What is bottom side? Gate and source are grounded. Incrementally, you just have only the R naught of the transistor. What is the total resistance? A series combination of the two. That's all. And this is what I meant by you try to find it qualitatively, right? You see a circuit, okay, first time you see something like this, you go and try to analyze it. And even when I analyzed it, I didn't sit and write KCL, right? So I sort of used superposition in a lame way and got around by. So here I didn't sit and write KCL, right? By inspection, I was able to write things. I mean, in the beginning, you might not be able to do it, but to try to develop that, right? That makes things quicker. And once you understand what that guy is, whenever you go and see this guy, you should go and replace it with the resistor. And another thing was this. So where I think something like this was given. So how do you solve this? Yeah, basically, again, if you see, this is a resistor. Yeah, it's a common gate, but this is, let us say, Rx. What is the resistance looking here? This is a cascode. So you just use the expression approximately whatever GM R naught times Rx. The exact expression is, see, you should always remember the exact expression and understand when the exact expressions can be approximated. It is good to make approximations, but it is very crucial to know when the approximations are valid. Okay. Huh? This one, right? Yeah. It all works out. That's the thing, right? That's why I try to explain you this way. This is a one port network, right? If I basically take this, you calculate it, otherwise also you'll get the same exact expression. So this is a one port network. Across this, if I apply any voltage, the current is going to be that calculated resistance times in the whatever V is IR, right? So this one port network, I can replace it by its one port parameter. That one port parameter is a resistor. This gate terminal. Which one? Upper terminal, upper MOS or lower MOS? Huh? If this is grounded, I mean, then it's not a. I mean, then the circuit itself is different, right? You're saying like this. No, then this is no longer an actually whatever one port network, right? You have three ports to access. I mean, three terminals to access a two port network. And let's say you do this. He asked you, let's find this also. This also should be able to find now. How would you find this? What is the resistance looking down? Okay, I'll take it to next page. Hold on. What is the resistance looking down? It's a cascode. You know the resistance. And then you have R and that R cascode. What is the resistance? Series combination of the two. You work it out. What do you want to say? Whole thing flips meaning? Okay, that also you work out, right? I mean, this one. How can you find this one? It won't be the same thing, but again, you can compute. Hey, see, the point is, remember that only if we have a two-terminal case, it can be replaced with a single resistor. Otherwise, it cannot. So here also you should be able to work out. Okay, I mean, I'm not doing it. It's again a cascode. So I'll stop here. I mean, TS will be around for some time. Hmm? Hold on, let me just see if the recording happened. Hopefully it did. Yeah.